Everybody knows Albert Cohen, so he has been here several times. I don't know, maybe 70 times. I don't know, maybe less. And he will talk about reduced modeling for manifold sensing.
Okay, so thank you for inviting me and giving me the opportunity to pay tribute to Wolfgang and Pencho. They've both been a big inspiration for me, each in their own way. I tried to find a picture with both of them. It was not so easy. I mean, I interacted with both of them many times, but the one I found was this one.
Yeah.
Do you remember where this was? Maybe Pencho, this is a quiz for you. Do you remember? he would know.
You know?
That's a quiz.
You should. One of the rare occasions where I really had a good soup.
Yeah.
And a pie.
So this is in Aachen, actually. This is in Aachen. This is when Ron got an honorary degree. Actually, Ron got an honorary degree from Paris now, just a month ago. He's collecting them. And so on the left there is Gérard Kerkacharian and Dominique Picard. Pencho is dominating everyone. And there's Ron and Wolfgang and myself. I think that was 2005 or something around that. Maybe six, maybe, yeah. Okay. Okay, the other thing I found, so in the time where we were all gathering here with IMI activities, there was this card game which was very funny. I brought it with me. So this is it. And so you have, do you, I don't know.
This is how you dress in private.
Yeah, exactly. I think even better. Okay, and so the game now, you have to, the quiz is who is who, because I have many of them. So there's at least maybe 5, 6 people in the room who are in this game. For example, and you can try to solve the inverse problem. What card is wrong, for example? It's easy, actually. He's the Joker. I'll show later for those who want. Okay, so the title was Reduced Model for Manifold Sensing. This is a bit general. Actually, it's the idea of manifold sensing, by which I mean you have some manifold representing some low-dimensional phenomenon in a very high environment, and you want to sense them by projecting on some low-dimensional space, collecting information. I came across this line of thought in a paper by Rich Baranyuk and Mike Wakin from 2007 FOCM paper, and it was about generalizing, the idea in compressed sensing, which is let's try to capture sparse signal for random projection, by saying instead of looking at sparse signal, we're going to look at signal which are represented by a low-dimensional manifold. Okay, sparse signals are more living on unions of low-dimensional spaces, but that was the idea. And here my motivation is completely different. These low-dimensional manifolds represent solution to certain partial differential equations. This has been motivated by a number of work we've been doing lately, and so engineering applications, and then the idea of reduced modeling comes out naturally, I will explain. Okay. So what we call parametric partial differential equations are, generally speaking, something I represent in this form. Okay, this is completely abstract. U is your solution to the PDE. A is a parameter, which means every time I specify the parameter, I have a different PDE, and so I have a different solution. Okay, so you can think of the dependence of U from A under the umbrella of the implicit function theorem, for example. And I'm going to give a typical example in 1 minute. So we have in mind many, general setting, but where we want to understand complex processes that are where the state changes depending on the parameter that could reflect the physical properties of the system. But we're always going to assume well-posedness, so we have a class A where the parameter lives. By the way, the parameter is typically going to be a function. And every time I specify A, that's going to be a unique solution. Let's say in some Hilbert space V. And so we can talk about this map, parameter to solution map. And the manifold will be the range of this map. So the collection of all solutions as we vary the parameter. So in general, it leaves, you can think of it as a manifold immersed in this usually infinite dimensional Hilbert space. And in most relevant application that I have in mind, the manifold happens to be a compact set. This will be of importance. Okay. So I'm going to explain the problem I want to consider, the state estimation problem. And then we're going to discuss an approach which was initially proposed by Yvon Madet and Patera, and then analyzed by us, but also by them, about using what's called reduced model to solve this problem, and that's what we call the one-space algorithm. And I explained how this is inherently limited through the notion of Kolmogorov width, and I'll talk a little bit about Kolmogorov width for these manifolds, and then I'll try to go beyond this by going nonlinear, and nonlinear approach, nonlinear reduced models, and this is ongoing work with the authors that were quoted, my collaborators that were quoted in the first slides. Okay. So let me give the very basic example, which I got in already many talks, but I think it's a good example to have in mind, and later I'll give a result that really applies to many other type of equations. So here I'm thinking of this diffusion equation. A is my parameter, so I think of the parameter to be the diffusion function, and U is the solution. Of course, you have to put some suitable boundary condition on your domain. D here could be 2 and 3, it's a physical domain. And so, in order to make this problem well posed, it's very natural to ask typically that the diffusion parameter are functions which are bounded by below to have ellipticity. So let's say bounded function on my physical domain that are bounded by above and below. That would be my natural class, but it's going to be also interesting to add smoothness condition. I will talk about it later. But as soon as you are there, you have well-posedness in the space which is now the natural space is the Sobolev space H10. That's what we will call V in that case. And sometimes in application you are actually given a more specific parametrization through scalars. So imagine, for example, that this diffusion function is piecewise constant on different area of the domain D. Then the natural way to describe it is through the values of the diffusivity on the various part of the domain. Okay, and in that case, you would typically think of it as an expansion, where this psi j here, this A bar would be a nominal diffusion, and this psi j would be, in that case, the characteristic functions of these subdomains, but you could have many other options. And actually, the number of these parameters could be infinite. Okay, and up to renormalizing this psi j, generally you assume that these y are in minus 1, 1, all these yj. Okay, so in that case, the solution map is in fact what takes these scalar parameters, this vector, into the solution through this diffusion, this form of the diffusion function. Okay, that's one example, but we could have many other in mind. And now, the type of problem I want to address are inverse problem, where we know the governing PD, like in the previous example, but we don't know the parameters A or Y that gave rise to the solution that we are trying to capture. Okay? So in the case of the diffusion equation, that means the diffusion property, for example, of the underground layer could be unknown to us, but we are still able to collect some measurements of the solution. So how do we describe this information? So we're always going to think of the measurements to be linear forms, bounded linear form on the space V. And this is our information now. We suppose that we have access only to partial information. Let's say we have sensors. We drill here and there. And this is represented by this Li of u for I equal 1 up to n. Okay? And now our goal is to best possibly combine this information with the model that was described before in order to reconstruct either the state u or the parameter y, a. So the picture we have to keep in mind is the following. You have to mark it. I write it here. You start from your parameter a or y, and you have this map taking you to the solution. It lives in this manifold. Okay, this map is usually a nonlinear map. And then you have these linear measurements that make you land in Rm. So let me collect them into one single vector, all this Li of u of A. This is a vector in Rm. Okay, and you can either think of the state estimation problem, which I will mainly talk here, which says let's try from this information to recover the state, u, or let's try to recover A, which is a parameter estimation problem. Okay. So this is you see that the state estimation is a linear inverse problem. In principle, it's in a way it should be easier than the parameter estimation, which is a nonlinear inverse problem. On the other hand, it's an inverse problem where the prior information lives on a very nonlinear set, which is this manifold. So it makes it equally complicated. Right. So there's a lot of course, work being done and on this problem, and I want to draw a distinction between different philosophy, different types of approach. There's a big amount of work on probabilistic approach, which I refer to as Bayesian inverse problem, where what you model, the way you model the prior on A or the prior on U is through probability. Okay? So typically you're going to use a probability distribution defined on A, which induces a probability distribution on U, in order to say that certain solutions or certain parameters are more plausible than others. Okay? And then what do? You try to estimate from your observation the posterior distribution, so the conditional probability with respect to the observation, in order to define the most plausible solution. And there's a very nice survey on all these methods by Andrew Stewart. Okay, they can be quite costly because every time you have new observation, you have to sample this posterior distribution, and this is one of the big numerical, let's say, not difficulty, but the big numerical budget is spent on trying to sample this posterior. And here I'm going to work in a different setting. So we are going to use a completely deterministic approach. We will not assume any probability distribution. All our information is that you live on this low dimensional, could be not so low dimensional, but manifold, and this is what I want to explain. Exploit, nothing else. So the way we're going to model now the information is by remarking that we can express this linear form Fourier Riesz map and define the measurement space as the span of this Riesz map. Okay. So when you collect this information, it's just equivalent to collecting the projection of this manifold onto a W. So you have this complex solution manifold somewhere inside V. It's high dimensional, and what you do is you just look at the projection of this thing on a low dimensional set space W. Okay, and this is what you see. Okay, and now what we call a solution algorithm. It's going to be a computable, a map which you can access easily by computation. That you can think of it as a lifting, because what you know is just a projection of the unknown object onto W, and you try to lift it into a reconstruction. So you try to add something typically from the orthogonal complement, and now you are really in the setting of optimal recovery. The question you can ask yourself is how can you choose this lifting in order to make this error uniformly small over M, as small as possible. Okay, that's what you would like to do ideally. So this is the deterministic setting I'm going to work with. All right, so where does reduced modeling comes in? The solution manifold is quite complex. Its description is usually not going to be accessible to us. And the problem of optimal recovery, finding the complete optimal algorithm, will not be easy to solve. I will return to this in the end. But for now, we would like to simplify. One way to solve this problem is to cheat a little bit and to say, let's replace this complex object by a simpler object. How can we do that? Well, reduced modeling methods are going to help us identifying linear spaces, Vn, that are not going to be exactly equal to M, but are going to approximate M up to tolerances epsilon n that that go to 0 as n grows. Okay? So what do I mean by this? I mean we have a sequence of n-dimensional spaces, and the distance from u to Vn is uniformly bounded by epsilon n for all u in n. Okay. Now this is very general. You could say why we know how to do that. We could do this with any types of finite element, polynomials, trigonometric polynomials, your favorite approximation spaces. But in that case, in general, this epsilon n might not go very fast to 0. So the whole game with reduced modeling is to try to build these spaces in a way that they are as much as possible tailored to the physical process, to the solution manifold. And one way there's, let me quote two modern ways to do that. One way is to, in the case where you have these scalar parameters y, is to make an expansion of u in terms of y, for example, a polynomial expansion, okay, and truncate this expansion into n terms, okay. So since u of y takes its value in a space V, this polynomial, its coefficients are functions in V, and this object for any y takes its value in the span of this coefficient, which is an n-dimensional space if you retain n terms. And now this is a very interesting space to work with. It's because now it's tailored to the process, to the manifold. Another way of building a reduced model is the reduced basis method, where the idea is just to say let's take snapshots, which means let's take a few guys from these manifolds, n of them, and just build the space Vn as the span of these guys, okay? And then there is a very interesting analysis there on how to select these guys so that essentially you find the best possible n-dimensional space. The best possible n-dimensional space is the one which achieves the accuracy of the Kolmogorov n-width. We'll talk about it later, but this is not something we can access in practice. Okay. So these are reduced models, and the idea now is to say, okay, let's forget about this M and let's now replace the assumption that U belongs to the manifold by some simpler assumption on approximability, which means we look at this containment set, which is a cylinder, okay? And this is what we call the one-space model, because we pick a certain Vn, we have a certain accuracy, epsilon n, okay? And now we forget about M and we say all we know is that U belongs to this cylinder K. Okay, of course, you could, there is a trivial generalization, but it is important in practice, which is that usually this M is not centered around the origin. Typically, if you think of this nominal diffusion, there's going to be a nominal solution, U bar. And then it's a rather wise thing to do to say we're going to consider affine space instead of linear space. But the analysis will be exactly the same, so our discussion will carry over. So it just means that you move this cylinder, okay? Okay. So this is now our prior, and now the geometry is quite simple to see, because what is your knowledge? Your knowledge is that U belongs to this space, and on the other hand, you collect this information on its projection. So if you fuse these two information, that means that you live in the intersection between this high-dimensional cylinder and this affine space, which represent all the functions that explain, that can agree with your observation, which I call VW. And so you live in an ellipsoid, you see, KW. Okay. So, obviously, all elements from this ellipsoid will be assigned the same approximation, and so you have an ambiguity. You cannot resolve several guys which are inside there. So obviously now you can exactly say for this model K, if you replace this M by this model K, what is the optimal algorithm? What is the optimal recovery algorithm? Well, obviously you should take A of W to be the center of this ellipsoid. Okay? This is what we call the one-space method. And actually, this one-space method was imagined by this author in their paper without taking this interpretation, but just by saying that what they propose to do is really to say, let's take as a reconstruction the U that minimize the distance to the space Vn for all between all possible U that explains the data. Okay? And this exactly coincides, not difficult to see that this coincides with the center of this ellipsoid. Okay? So what's nice about it, it's just a least square problem because everything is done in a Hilbert space. Here you can actually generalize this idea to planar spaces, but then it's not as computationally friendly. And another interesting thing, so it can be computed by linear systems, simple linear system. It does not require the knowledge of epsilon n. Here it seems the way I defined it that this will be depending on epsilon n, but if you see this formula doesn't depend on knowing epsilon n. It only depends on Vn. So that's sort of nice. And now what is the accuracy of this? Well, you can immediately see that what's going to count is the geometry between the space Vn and the space W, the angle, to understand whether this thing is, in a way, if this ellipsoid is well conditioned or not, if it can be very long and thin, and this is simple to describe. So this is going to describe by an im subconstant, which is this quantity, but it's best to look at its inverse. So you actually take the supremum for all V in Vn of the norm of V divided by its projection onto W, okay, which is always something bigger than 1. This was actually introduced in another slightly different context by Adcock and Hansen. Okay, but it's really an angle, and you see, for example, so what's going to happen with this? What we are able to show once you define this condition is that the supremum of the error for all U in K of reconstruction through the algorithm that I gave before is bounded and actually equal in the case where you took really this containment set K to be your model to this epsilon n accuracy, but this is multiplied by this constant which could be larger than 1 and which reflects this angle. Okay? So let's look at this constant. It's always bigger than 1. You will have equality to 1 only if your measurement space contains the space Vn. In that case, it's obvious that this is 1. But you could be much larger than 1. You are actually infinite as soon as Vn contains objects which are orthogonal to all the measurement, because then you have complete ambiguity. And so this happens in particular when if you have not enough measurements. Okay, so you're always here in this setting. You're always in an overdetermined setting. You assume that m is bigger than n, And now you see that those two quantities, now you have two quantities that goes one against the other. Epsilon n is going to 0 as n goes to infinity, but mu n is growing. Okay, so you have a trade-off that you can try to optimize. Okay, because as n grows, eventually you become infinite, and as n grows, you look at the supremum in a larger and larger set of functions. Yeah. Okay, so that's what's been established for this method, and let me give one instance where you can see what happens. So in that case, this is a parameterized elliptic diffusion equations, and the measurements are local averages at certain locations. Okay, and now what you see here, let's see. What I'm showing you is here first the projection error. So that's just the accuracy of this reduced basis space. If you use different choices for this space Vn, this is with standard models, like finite element. I think one is finite element, one is Fourier. And this failed to capture the singularities which are due to the jump in this diffusion coefficient. And this is, unfortunately, I think you don't see this, but this is something like 10 to the minus 6, I think, and 10 to the minus 1. And this is what you obtain with reduced basis. So, of course, the projection is much more efficient. But then you have to look at what happens with these in subconstants. Okay? And actually goes to 0 faster with each choice than with this choice. So there's going to be still something with the trade-off. And if you look at the reconstruction error, still what's happening in that case is that the accuracy here is so fast that it still allows to compensate. So this is with reduced basis, and this is, I think, with sine or trigonometric function. And that's the reconstruction error. This is the recovery, which you manage to continue to go down as until you reach until n, the dimension of Vn, reaches the limit value m. And here you will eventually get very unstable because the decay of this thing will not be able to compensate for the growth of the inverse in subconstant. So definitely the reduced model approach is better in that case. Okay.
Can I ask a
please.
couple questions?
Sure.
So in this case, the uniform ellipticity constant is 0.1?
Yes, exactly, 0.1.
That is that for those that aren't following, that the A can take values as close to 0 as 0.1, and taking values close to 0 is a problem because you're losing ellipticity.
Yeah.
But on the other hand, that's where the singularities. I mean, there are no singularities inside the parameter domain.
No.
They all occur outside.
Yeah.
And so you want to magnify the performance between greedy and other methods. Don't you think it happens by pushing these singularities close to?
Sure, I think this is
That's what we found.
Probably if I put 0.99, then you will have even a stronger discrepancy between the two. I agree. On the other hand, the inability of Fourier is not only due to the problem of lack of ellipticity, but just to the lack of spatial smoothness.
Lack of what?
Of spatial smoothness. Okay, that's where Fourier, for example, plays. Okay, while the singularity, the spatial singularity, are sort of they are taken into account in the reduced basis method because the reduced basis already
They come
have
from the
okay
manifold.
contain, yeah. Okay. So now I presented this thing as if these spaces Vn and W were fixed, and now we can do a number of things based on that. We can try to say, okay, we can try try now to make this a little bit more optimize this, and we can optimize in many ways. One first way is to say, okay, give me this reduced model space Vn, and you say, okay, I would like to select. I would like to select good measurements. I want to, let's say Vn is fixed, but now what's not fixed is what is my measurements. Okay, that's maybe close to the compressed sensing philosophy. How should we measure? Sometimes we don't have the choice, but let's say we have the choice. For example, we want to know where we should put our sensors. Okay, so it means we cannot take any linear functionals, because in that case you would just take the linear functionals that would be an orthonormal basis of Vn, and you would just get the error of projection onto Vn. Okay, so it's better to say, let's say we have, it's more realistic to say we have a dictionary of measurement functional, and we want to select m of them. Okay, and so if we are decided to use the space Vn, then of course what you have to do is to try to make them, select them in order to make this mu, this inverse IMSU constant as small as possible. Okay, so trying to guarantee, let's say, a lower bound on the IMSU constant. Okay, and this is not such a trivial problem. Okay, first it's trying to find the absolute. If you, let's say, imagine you have a huge dictionary. You have 10,000 possible linear form, and you would like to select 100 of them. This is in general going to be a highly complex problem, and you can try to at least approach it by some greedy method. So what would be the greedy method? Let me explain how it relates to greedy algorithm that, for example, much studied by Volodya. If you think of what this mu is, what is this beta, what is this mu? Yeah, this beta is, you look at the inf, and you check, or mu, let's say, yeah. You look at the inf between, I'll take mu. Mu is the sup, and you have V divided by its projection onto W, right? Okay, when V is in Vn. Or you could just put 1 here and say that you look at V in the unit ball of Vn. Okay, and say what you would like is that this thing is not too large. So what you would like is to make this thing PW objective. Your objective would be to have PW V larger than some fixed alpha for all V in Vn such that norm of V equal 1. Okay? So you would like that this projection capture at least a certain portion of the energy. And you see this is just equivalent to say, try to build this space W in order that V minus PWV for all these V in Vn such that norm of V equal 1 is less than some gamma, where gamma is square root of 1 minus alpha square. Okay? So now you see what you're trying to do. You're trying to capture not only one single V, which would be what you do in the usual greedy algorithm, where you try to select elements, but the whole collection, okay, which is this whole unit ball, okay? And so we call this, so you can mimic the idea of greedy algorithm. We call this a collective greedy algorithm, and I think those who know greedy algorithm, orthonormal matching pursuit would immediately think of how you can do that, and you can try to analyze this, and this is what we have done. So we have a greedy way to do that. The other possible way of optimizing is, let's say now our measurements are fixed, you don't have the choice. We have fixed the sensors, and now the question is, how could we find a space Vn which would optimize the final performance? So you remember that you have this epsilon n and now the first thing you could say is, let's take this reduced basis space and try to minimize this product among all of them. Okay, so try to find the value of n which minimizes this. We call this a poor man algorithm, because you can obviously do something better, and you can even actually try to find an optimal space Vn. The way you can do this is through a sort of learning process, by taking many offline, by looking at many possible samples from the solution manifold, and use this data in order to construct essentially a best defined reconstruction map, which turns out to be really equivalent to construct an optimal space Vn. So you can do these two things, and we have a numerical experiment that show that this is a wise idea, but there are some interesting limitations. So the one space method, so far what I showed you is that you replace this complex object by a very simple containment set, a cylinder, for which optimal recovery can be carried out by a simple algorithm. But it's essentially a linear or an affine method. And because of this, its performance will be limited by below. Right, because you end up, because it's linear, you end up in a space of dimension m, because you start with m pieces of data. So the range of this map is a space of dimension m. So certainly you will never do better than what you can do best to approximate the solution manifold by a space of dimension m. This is what we call the Kolmogorov m width in that case. And this limitation can be also expressed by the fact that this containment set is convex, so you cannot really capture the geometry of M. So our goal now is to sort of break this limitation, but you have definitely to turn to nonlinear algorithm and to non-convex reduced model. Before I go there, let me say a few words about this question of Kolmogorov width of solution manifold, because Kolmogorov widths have been highly studied for classical sets, compact sets like unit balls in smoothness classes. We all have learned this in approximation theory, and but never for these types of solution manifold. So how can you estimate them? Let me give you, so you would like to have an idea what they are in order to understand what is your limitation, what is your bottleneck. So first, if you try to find upper bound, one way, which happens to be effective for these types of parametric PDEs, is to understand it from the smoothness properties of the parameter to solution map. So here's a theorem that we proved with Ron a while ago that says the following. So think of this solution map now, equip the parameter space A with a Banach space structure, X, and think of A to be a compact, the parameter domain to be a compact set in this Banach space. and assume that U is a bounded and holomorphic map from X to V when restricted to this parameter set. Then what does this theorem say? It says that essentially the decay of the Kolmogorov width of M can be inferred from the decay of the Kolmogorov width of A. Okay? And it says actually that this, if dn of A decays like n to the minus s, then dm of A will decay like n to the minus t for any t up to s minus 1. Okay, so we have a little loss here. If you think of, if A was a linear, U was a linear map, obviously you would have the same decay because you would just take, for the linear space, the image by U of the linear space for A will give you a good linear space for M. Okay, so there is something non-trivial in this result, and it would be very interesting to understand if this decay, this loss is sharp. If anybody has an idea, actually the way we prove this result is through these polynomial approximations in high dimension, and maybe there is a much more elegant vehicle to do that, but we didn't find it. So, for example, this applies to our problem because in that case, my example problem, it's obvious that the dependence from of U2 from A is holomorphic. And what could we do? We could obviously, but you have to take X to be L infinity. But now you want to take compact set in X. So, for example, one way to consider compact set is to impose a smoothness condition. So here I'm taking A to be less than 1 in HS. So I call this a class AS, and by taking S bigger than D over 2, you have a compact set, and you even know its width. I think this is a very nice result by Kashin, right? Which is surprising, in fact, if you think about it. But as soon as S is bigger than D over 2, you have this width. So you have the rate. So immediately you derive from this a certain rate. And now, is this rate optimal? This is not clear, but we can find a lower bound also for this rate. Let me explain something about that, which is not so not completely trivial either. So now you would like to say something. Do we have a rate by below? Okay. And the way you can prove a rate by below is by going through a lower bound using the entropy numbers. So let me recall that what we call the entropy number, it's the smallest value of epsilon, such that we can cover m by 2 to the n bolt of radius epsilon. Okay, you look at this epsilon cover, and you want to have at most 2 to the n bolts. Okay. So why is this useful to prove lower bounds on the n width? Because you have comparison results, what's called Karl's inequality. Karl's inequality gives you a comparison. Oh. Okay. That essentially says the following. I mean, this is a consequence of Karl's inequality. It says if the width decay like n to the minus t, then the entropy number have to decay like n to the minus t. So the rate cannot be better. And now, of course, you would like to have lower bound on the entropy number. So you're back to another problem. But now, how can you do that in this context? Well, you can do that by looking at the properties of the inverse map of this, if it exists. So why is this interesting? Because we have actually proved some result on that. So this is also some recent result with Ron, Andrea, Gagana, Garrett here. And here's a sample result. It says if you have a Lipschitz domain, okay, and if f is a positive function, then if you look at this class A1, if you think of H1 functions for the diffusion coefficient, then you have an inverse result that says the following. If the two solutions are closed, then those two guys, A and B, should be closed. But here you see you have a power 1/6. Again, we don't, well, actually this 1/6 will be sharp in certain, for certain cases. Okay, so then this is a way to prove something about the entropy number, because this kind of inequality will actually allow you to bound the entropy number of M by below by the entropy number of A. All right? Because you see, this thing is telling you that if you can find if you cannot find entropy numbers are about finding epsilon net, right? You want to look at you want to cover by guys which are close to each other by epsilon, and you don't want too many of them, okay? But if they are close by epsilon and you have not too many of them, this will be close by epsilon to the 6, okay? So it means that En of M in V is always, once you put it to the power 1/6, is going to be bounded by below up to constant by the entropy numbers of the class A1. And the entropy numbers of the class A1, now we know what they are. They are like n to the minus 1/d. Okay. So now, immediately you see that it means that in that case, dm of m cannot decay faster than this. Okay, and again, it's unlikely to be sharp, but we have an estimate by below. This is one of the rare instances where we can prove an estimate by below for this solution. Okay, so having seen that, you see that this justifies this objective of going to nonlinear algorithm. And let me, to start with this, let me formulate now what would be a general benchmark when we look for a general algorithm for optimal recovery. Okay? Well, what you can, since what we have is, what we observe is we have this solution manifold and we observe its projection. We're interested in understanding what is the ambiguity that we still have on the elements of M from this projection. So it's natural to define this diameter, this observation diameter, which is defined by the maximum distance between two guys in the manifold that have the same observation, so that their difference live in the perp of W. Obviously, any reconstruction algorithm will not achieve performance better than 1/1/2 of this, and this is your benchmark. If you have an optimal algorithm, you would essentially take an element that sits close to any U that has this observation to, let's say, less than 1/2 of sigma 0. So this is really the ideal benchmark, but this is not going to be achievable by a practical algorithm. Okay? Now, all these algorithms that I described are based on a certain notion of approximation, of trying to approach M up to some, take a certain offset of size epsilon, and replace M by this accuracy. So here's a more general benchmark, thinking that we are going to approximate M with some accuracy epsilon. We are going to say, let's look at the maximum ambiguity between two guys that have the same data, for which we observe the same data, but which live in this offset. And we call this sigma epsilon. And M epsilon is really M plus the ball of size epsilon. Okay? So this quantity in general could be much smaller than the Kolmogorov width. And this is our benchmark. Okay. So the most simple idea that I want to develop now to go nonlinear is to say, okay, let's, instead of looking at only one reduced model, let's say we're going to look at piecewise local reduced model by saying, okay, I want to use a certain linear space here, another linear space here, another linear space here, another linear space here. Okay? And they should all be of a dimension less than the number of measurements. So how could we do this? By a certain splitting of the parameter domain, which we can perform in various ways, but we can construct a family of reduced models, for example, by using reduced basis for this part, reduced basis for this part, and so on. Each of them of dimension. So that each of them will approximate the corresponding portion of your manifold with an accuracy epsilon k, and will have some bounded IMSUB constants mu k. Okay? I'm not saying exactly how this is being done, but it's not so difficult to see that if you take enough splitting, then you can always ensure that this thing will be as small as you want, and that this thing can be maintained less than a given mu bigger than 1. For example, take mu equal 2. Why? Because you could always go to a very extreme situation where you take an epsilon cover of your manifold. In that case, it means that epsilon is your accuracy, and mu k will be 1 simply because the spaces will be points, so they will be of 0 dimension, and in that case the IMSUB constant is just 1. But this is an extreme situation that we don't want to reach, because that would mean k would be humongous. Okay? So this is not what we are actually doing in practice. We are again building this thing by a sort of greedy splitting of the parameter space, and we continue until we have reached a certain accuracy. We are currently testing these methods. And now, what is the situation? Now we have different linear space vk. To each of them you have a one-space algorithm ak. So for the given data we have now many possible reconstruction ak of w. Okay? And of course u belongs to m, so it belongs to one of a certain corresponding portion, but for this particular k we know that this thing will be less than mu epsilon. Okay? So this is what we call an oracle estimate, because if we would be able to know, given your data, which part of the manifold it came from, then we would have this inequality, and you could make epsilon as small as possible. This is not feasible, because you have to know what is this k of u, you don't know it. Okay? So now we want to use our data for selecting a value which, hopefully will not be maybe the exact one, but we will do some good job. Okay, how can we do that? This is probably my last slide. Okay. So ideally, what could we do? We could we have all these different reconstruction, and one way to proceed is to say, let's pick the one that sits closest to the solution manifold. So try to minimize among all of these reconstruction try to minimize the distance to the manifold. The problem is that this is not exactly computable because you would have, this is extremely complex, you would have to perform this minimization, and again, this would amount to compute all this solution by some numerical solver. This is not something we are decided to do. But again, if you look at the instances that I gave, you can do something a little bit more friendly. Why? Because you can replace this quantity by the residual of the equation in the dual norm. If you have in mind the elliptic equation that I gave. So in that case, what would be this residual? This residual in the example that I gave, taking divergence of A grad AK of W plus F, and looking at this in the dual norm H minus 1. So why is this a more friendly problem? The reason why is because now you see that this residual depends in an affine manner on A. Okay? So this is just now a convex quadratic function. And you can minimize it by many simple routines. Okay. And this is more or less equivalent because when the problem is uniformly coercive, like what Ron remarked for this problem, where you have this ellipticity constant, uniform ellipticity constant, then essentially these two quantities are equivalent. So you will always have this thing once you select the value k star that minimize this distance. So the program is now compute all this for the different k and select k star minimizing this quantity. And now the theorem is the following. The following theorem is saying that once you do this selection, now you have the following estimate. So I don't know if one sees exactly what this is. So what is this estimate? This estimate is not the oracle estimate. You will never reach the oracle estimate. So remember, the oracle estimate was this. But what's going to appear is this this quantity sigma. Okay, this ambiguity radius, and what you have is sigma. But instead of epsilon, you have mu times epsilon, and maybe this is a constant. Sorry, this is quite fast. Okay, so I think I'm done. And so the conclusions are the following. So you have a nice linear methods which amounts essentially in solving linear system, but which amounts in doing optimal recovery in a simple convex cylindrical containment sets, completely suboptimal over the true solution manifold. And our goal is to develop this nonlinear algorithm. I gave one approach which we are currently developing. Another approach is to think of this as a model selection strategy. And you could try to borrow techniques from statistical learning, for example, aggregations of these different estimators. There are also analogies with this Bayesian framework because linear reconstructions are essentially what is produced when you are thinking of your prior distribution as being Gaussian. And nonlinear means that you are considering non-Gaussian framework, and one simple analogy with this piecewise linear modeling is to do a mixture of Gaussian models. Okay, so I think I'm done. These are a few references. The first one is the one I mentioned about random projection on smooth manifold, which I think is interesting because it goes in this line. This contains the result of on approximation, and in particular this result on n width, how the n width of the parameters domain is transferred to the n width of the solution manifold, and these are reference on this one space algorithm and how you can optimize it. And last but not least, yes, this is my card. Thank you.
Okay, questions?
Well, so, I mean, I'm doing this for the audience purpose. I mean, the main thing you didn't cover is how do you break up the parameter domain into these.
Yeah.
I mean, your starting point is that you have such a.
Okay, so in this, you're right. I mean, this is so we have debated that many times. Yeah. So we, if you think of this parameter domain, as I say in this example, this parameter domain is really this cube Y, okay, which is a j-dimensional cube. And the question is how to split it, okay? So splitting, high-dimensional splitting is a problem, right? Because if J is large already, if you do quad split, you're going to have... So, you know, one way is to say we can split in... The first step of the greedy will be to choose between splitting horizontally or vertically to say, are we going to do that or are we going to do that? And our decision will be based on this quantity mu and epsilon that we find in the two scenarios. So we're going to do that, and then we're going to pick one, and where the product between mu and epsilon is the worst. Okay, and we're going to continue. Okay, in that case, that would be. So I'm not giving the detail.
Each cell separately.
Huh?
Split each new cell separately.
Separately. Each new cell will be. Okay. Now, this is not such a bad idea because the idea is that the algorithm should be able to discover what are the most sensitive variable and tend to perform more splitting in this variable than in the others. Okay. Now, you know, what is the bench? By the way, if you talk about approximation by saying we want to do approximation by k linear spaces where we decide what they are, there is also a benchmark for this. If you just talk about approximation, not recovery, forget the measurement. This is this notion of library width, which is from your work. And library width means, for M, means you allow any type of let's say, n-dimensional spaces, but you can take k of them, okay? And that means that, in fact, you allow complete arbitrary partitioning. It's extremely wild, something that we cannot afford to do numerically, okay? So we will never, we do not hope with this type of splitting to get to. This is an interesting thing because with the usual reduced basis algorithm, without any splitting, we know that we can do as good as the n width in terms of rate of decay. That is something we proved. And we don't have any analog for library width. I think it's a bit too ambitious. Okay. Yeah.
You know what would be interesting to see, just to get a feeling, there's nothing I could say rigorously about it, but maybe James has set it up. If you combine this parameter domain decomposition with an intermediate projection of that optimal parameter doing this least squares problem, then you take as your next local reduced basis just the Taylor basis.
Yeah.
And for the Taylor basis, you can take for the split direction, the one where the measurement is largest.
Mm-hmm.
So this in a way you go for a very close linear subspace approximation form.
So
This, that would save you the greedy search and.
yes, there's all kind of variants also, because what you mentioned is, I think you have something a bit different in mind that says, given your observation, you want to make a splitting that depends on your data.
Yeah.
In this thing, the splitting is
That
done
you do it
prior
in the
release,
space.
okay, and then you receive your data and you use what you have been doing. Okay, that's interesting. I mean, this is a question of. How much on you want to make here a distinction between the online
Yes.
and the offline cost? Obviously, you are allowed to spend quite a bit of time offline as long as online it doesn't take you too long. Yeah.
Other questions? Not. Let's thank you for